This is provided from the Institute of Indian Foundrymen, Chennai Chapter and Andhra Chapter. The topic for the day is controlling casting rejections through effective core shop management practices. And with us today, we have Mr. P Mathew. He's Solution Manager at Foseco. And to give a few words about him, uh, uh, he's done his master's in polymer science, 1997, University of Pune. He has around 25 years of experience in Foseco India Limited.
Thank you, sir. Thank you for the introduction. Hope my voice is audible.
Yes, sir. Your voice is audible, sir.
Mr. Mathew, hold on 1 minute. Hello?
Yeah.
Yes, sir.
So before that, on behalf of Andhra and Chennai chapter, we welcome all the fellow foundrymen for this webinar. Core shop is the very vital area where the defect happen in all the castings, predominantly for 50% of the defect. So where we couldn't able to find whether it is core shop inclusion or mold inclusion, there we need technical skill, some expertise to find the reason where it occurs and to take the appropriate root cause. Actions for the root cause. So all those things are the need of the hour. So for that, core shop management for handling the core shop defects in casting, Mr. Mathew is going to give a very wider presentation. I request all the participants to attend the program fully, and whatever may be the questions can be asked at the end of the program, and Mr. Mathew will be in a position to give the answer for all the questions. Now I request Mr. Mathew to take their on. Thank you.
Thank you, sir. Thank you. Okay, good afternoon. And
good afternoon, sir.
Good afternoon and welcome to this short session. Okay, Raman sir had already introduced the significance of the subject and the topic, but it's a vast area and it is very difficult to cover in 35-45 minutes. So I am giving you a bit of glimpses. Possibly this can be a three or four sessions, but within the given time, I will able to cover at least 30 to 40% of this today. We'll see how it goes effectively. If it is effective, you feel it is effective, we can continue this session for one or two more sessions. With this, let me take you to the background. The background to this session, because the foundry industry and my topic I felt is a little very wild, and I need to be very specific about from the beginning itself. So India being the second largest casting producer, roughly more than 11.5 million tons of casting being produced. And so we are the second largest or third largest. So there is still a dispute. Okay, whatever be the case, it is more than 11 million tons, and I am taking it for a rough approximation as 10 million tons. So out of these 10 million tons, 90% are ferrous castings, that is steel and iron castings put together. So the remaining 10% we can say it is non-ferrous, which is predominantly dominated by aluminium. So from out of that 10 million ton, roughly we can say 9 million of ferrous castings. Out of that 80% is iron castings. So that is the SG and ductile iron castings is amount to 80%. And if you further bifurcate it, 50% are small to medium size castings used in auto and agri segment. So I am again excluding here the big windmill foundries producing SGN castings and ductile iron foundries who is producing a large volumes of castings. Whereas the core applications, it is done in different platforms. One is centrifugal casting, one is the no-bake lines where you make the bigger castings for iron. When it comes to iron, talking specifically to the casting produced in the green sand molding process, these are classify it as a small to medium size, which a few grams to maybe up to 100 kilos of casting weight range. So for these castings, if you look at this 5 ton, roughly there is 2 ton of cores used for producing this 5 million tons of casting. We are using almost 2 million tons of core. That is equivalent to almost 10,000 trucks of silica sand. Considering a 20-ton truck of silica sand, almost 10,000 tons, 10,000 trucks of silica sand is used for core making only in India. That is amounting to almost 600 crore annually. And if you look at from the spend perspective, it is 1.7% of the foundry spent only for core sand. I am talking here only about the sand, not even about the chemicals. This is only 1.4% of the casting spend is on sand. And for core making, if you consider the molding plus core making process, the total new sand used, the 60% goes to new sand or core consumption only, core making only. For this core making, now I am very specific about the small to medium foundries. The major binder system used is polyurethane cold box process. So known as normally people call it a cold box process. We have shell coating process which amounts to almost 29 to 30%. And there are other like alkaline phenolic process or eclotec, which amounts to 5 to 7%. And other air set systems amounts to 3%. So if you come to that, almost 1.10 million tons of cores are made with the PUCB, that is polyurethane process itself. So my presentation today will cover mostly about polyCB process and the core shops. When I say it is mostly about polyCB process core shops, because Ravens are already said core have a direct linkage to the casting quality and what are the aspects we need to look into it. So it consists of 3 parts: casting quality and process consistency have basic functional components for the foundry. In the resin and we need to achieve by addressing the issues related to the complexity of the cores. Resin is based on phenol for shop scrap. Phenol for the 3 major areas dissolvent differently aromatic and aromatic quality and process consistency. So addressed by addressing is based on methyl diisocyanate and part scrap and complexity of the typically the ratio of 1:1 we can use. That is meet the functional requirement to be used on the shop floor between A and B. That is how we had come to this topic of first class mechanically as well as process. So this introduction we get into that. Major advantages we come all have selected the casting quality advantages. Casting quality is getting affected because of the casting defects, which may which may lead to a
Mr.
rejection
Swaminathan
or a
Shivakumar,
rework of
please
a
mute your
casting.
mic. It's
So these are
interrupting
the
the session.
broad
Thank you.
spectrum of
Swaminathan
casting
Shivakumar,
defects you come
if you're
across in the
listening,
foundry,
please mute your mic.
which will have a certain contribution from the core side.
Or Shekhar sir,
One is a
admin.
gas defect or pinholes, we can say. Yes, core shop, the way we select the binder, the way we do it, it have a relation to that. The way every binder gas system is a trade-off. We have advantages you are seeing is relation to the production time, productivity and low cost. But the way we do the major shortfall, we can say the shortcoming of the system is process of nitrogen in the system. It have a direct linkage coming from the fissures. When we are talking about the fissures, is about nitrogen diisocyanate, which is a dominant. Typically, the part will have 7 to 8 PCB process in the 7 to 8% nitrogen. Iron automotive foundries and sanding lutions or any metallic at the rate of 1% application, which is on the core side the sanding lutions. Then scabbing will have 0.7 to 0.8% of nitrogen. We may lead to the rejection of the casting. Melt naturally will have is a defect which is very frequently we come across, but it's managed with the welding, with the grinding. But if veining is in an internal passage area or inaccessible area, it becomes a big concern of reefer for us. Everything and also metal penetration. Core sand is getting diluted into green sand mold. Which fusion, which is further accumulate nitrogen in the green sand. But it is a combined to the penetration from the melt, from the core, from the green sand molding. it exceeds the threshold limit, then it will result to you as a nitrogen fissure. This if it is slightly on the borderline case, you may get nitrogen pinholing defects, and if it is on the excessive, only on the higher side of the threshold limits, and its root causes. Rather, we are going one step ahead and going to the area after machining. Looking at the mostly fissures may not be visible by naked eye, but and it's slightly after surface machining you will be able to see. And this is nowadays we should have looked at Indian foundries using PCB system. This is limitation of the time we are directly skipping that step to going to the direct. And also another major shortfall is the reaction with the moisture. So this is a part B disciplines can avoid this type of having multiple side reaction with the moisture. It can give you multiple byproducts. Anything undesired reaction can lead to. Somebody was asking very fast reactions, and which will give you very short bench life and strength loss. So that will result. We are talking about the complex core assemblies. So reaction of moisture and presence of nitrogen. Last 10 years we can see a lot of castings, and we have different a lot of amine to choose from. Difficult geometries are getting added to the production line. Like thin and complex geometries, like first one, try 3 mm to 4 mm section use across the globe, across India. Whereas in Europe, normally they for packages try to select on the multiple number of them or a packed together. First one made on different time, different machines. The need of high reactivity because of the low atmospheric temperatures, delicate climatic conditions, very thin and fragile sections over there. Because then also we have a very problem with controlling the temperatures section, but for them they having getting sand heated to the have its own complexities and challenges. So they naturally go for a very fast reactive, have different varying complexities and different challenges for Indian conditions. So each and every core we cannot look at it and make changes in the foundry. So we have to look at core shop as a entire entity and to the collective action, so that everything of these things can be taken care of 80 to 88 degrees centigrade. So that is boiling point of that. So that is this is how some correlation with our process. That is why I mentioned over here. Core scrap, it's a universal problem. There is nothing so polyurethane bond, but this is a universal problem. But it is an economic loss to everybody. And reduction, the part one which is core loss is a one casting production free hydroxyl group as the NCA. We are looking at polymer chain, minimize or eliminate the core scrap. Which will have a NCO. That is scrap can be because of many issues. The complexity of the core itself is there. When you think about the core assembly concept, that is why it is suppose there is a thin fragile core of 1 kilo. So with this much of rest of the core assembly, binder system 70 to 100 kilo. You can 1 kilogram, one small core getting damaged, and the assembly will not go into getting a 70 to 100 kilo assembly. That is just so you should not about 1 kilogram core damage. It is all about 100 kilogram. When you go to the core shop management process, so because process we need to look at the 70 kilo is what are the major getting scrap. Major aspects is one is so another contributing factor is the temperature and moisture. That's impact. There are making stages more like machine parameters and process parameters. Gassing, further core storage, core pressing, out of the box aspects we can further discuss. Today's session we will cover different stages of the process at the machine stage itself, or after the we look at the core making process. It is a very schematic process. Or at the handling and storage stages, liquid resin and hardener is getting coated with that. Then practice pass amine gas. These are the various factors which will contribute to the core scrap. Purge it out. So in the subsequent sessions, we will look at what needs to be taken care and some part of the solvent goes out handle all these issues. Polyurethane bond which is formed between the sand grains. The core shop management practices, the core we will look at the basics of polyurethane cold box system. This is PUCB. It is known as polyurethane cold box system. The major in the process, you know, it is almost polyurethane is the type of the bond being formed. Cold box is because it is cured in the cold condition. You will have the how the name comes in which how the core will be. In our terminology, it is a gas set system, and this system will work. That is why sand selection that will become the important aspect to consider under the sand grain. Under this aspect, we need to consider sand grain shape, grain fineness number, particle size distribution. Consider three parts means if have clay and fine, three component pH value, in the resin demand value, temperature of the sand, there is amine gas in the sand. These are the so this is a resin is based on take any big binder systems. People will talk about all these aspects, but dissolving specifically, and when you talk about UCT binary system, we are very particular about all these aspects because it is a very sensitive
hardener
system.
is based on
If I talk about an
and
white
part
binder
3 is
system,
amine
moisture
gas.
content, I may not
Typically,
give
the
that
ratio of 1:1
importance
to
or a
be
pH
used.
value.
That is
I
the
may not
typical
give that
stoichiometric
importance
ratio to be
because
used on the shop floor
the
between
inter
A and
system have
B.
the capability to
And
absorb.
the system can be reclaimed
with
mechanically
that.
as well as
But
thermally.
when we are talking about
And it contains
UCT binder
nitrogen
system,
from the part
this
B.
is very important. That is
Where
why
the
advantages
advantages
you
you
know you
put it.
all have selected because
So
of its
the first
advantages.
4 aspects.
So
that is
grain size, fineness, and particle density. This have a direct impact
on
on
the
the surface finish on the casting
excuse
from the
me,
core side
Mr. Swaminathan
and
Shivakumar,
permeability of
please
the
mute your
core
mic.
and the
It's,
core conversion.
interrupting the session.
When it comes to the
Thank you.
remaining set of the aspects like
Swaminathan Shivakumar,
properties like
if
pH,
you are
acid demand
listening,
value,
please mute your
temperature,
mic.
and moisture, it have directly impact on the mix and bench
Or
life of
Shekhar
the
sir,
binder
admin.
system, and also
Yes.
on the core strength. So the mix and bench life means this workability of the mix, the sand, or workability of the sand. The way every binder system has is a trade-off, from which you can advantages you are seeing is fast productivity.
you know the PUCB process
Typically we handle it as a same time the major
batch
process means we can say there's a shortcoming of the system percent of nitrogen in the
core out
system.
of it.
The
That
nitrogen
is how
coming
the
from the
comes
part
into
B,
play
that is
here.
which contain methyl
All these
diisocyanate.
two
Typically, the part B will have 7 to 8
contribute to the core scrap,
7 to 8%
productivity, casting
nitrogen.
defects, and cost aspects. Okay,
And
the mix and
if you
if
consider
low, your
at the rate
core
of
scrap
1%
naturally will
application,
be
which is
low,
high,
and
okay,
if it is low, your
then
productivity,
the core will have
frequent
0.7 to 0.8% of nitrogen.
and the core is friable.
You know,
can
melt
get
naturally will
defects
have
like
inclusion defects. Also, all these aspects contribute to your cost aspects because for the sand wastages, lower sand means your sand wastages, scrappage of the core, then everything is
higher.
not getting burned and core sand is getting diluted into grease and mold.
how
Which will
all this
further
accumulate
accumulate
nitrogen in the green
very
sand.
important. If the combined
Important
limit
influence
from the
on
melt,
the
from the core,
properties
from
of
the
the
green sand molding,
quality
of the casting, it exceeds
So
the
how it is
threshold
each and every
limit,
aspect,
then it will result to you as a nitrogen fission.
If it is
slightly on the
quality
borderline
of the
case, you may get nitrogen
So,
holding defects, and if it is
under
on the
the
excessive
best
only on the higher side
or
of the
the best
threshold limits, you will
practices,
see it as
we
a
are
deficiency
defining
defects in
it
the
as a
casting
sand quality
at the subsurface area
we
after machining.
always
Mostly
recommend you
fissures
to
may not be
wash
visible
graded
by
and
naked
dry,
eye,
but
silica sand with the
slightly
lower
after
fine surface machining, you will be able
of
to
core
see.
making. Very
And
generic
this is
statement,
nowadays
but
with the Indian foundries
this is any
using
supplier will
PCB
tell you
system,
this.
This is washed graded dry silica sand with lower fines and clay content. And what is the AFS requirement? And also another major shortfall is the reaction to moisture. So
Lower
this is
than
a part
that,
B which
coarser
have
than that
isocyanate, which is
you
having
need lot of
multiple side
biodegradable
reaction
moisture.
finer than
It can
means
give you
multiple byproducts.
biodegradation level also will go up.
Anything undesired
This
reaction
minus 150
fraction
can
and
lead
minus
to,
200 fractions, very
this
fast
needs to be
reactions, and which will give
strictly
you very
controlled
short bench
as per the
life and
specification, that is
strength
5%
loss. That will result to you as a friability and breakage of the
nil
core.
is the
So
desired.
reaction of moisture
As
and presence of
theoretically,
nitrogen is
there is
two
nothing
shortfalls
called
of the
nil.
system.
So we are allowing
And
say
we
it is
have
0.2%
different types of
maximum.
amine to choose from, which is I
And
put it for
ADV
academic purpose.
should
Nothing
be
maximum
great
6 to
about it,
7
but
ml of
exceptly
normal. The
sulfuric
first
acid
one, triethylamine, what is what
silica
we
content
commercially use across
higher
the
the
globe,
better,
across
but
India,
97%
whereas in
minimum.
Europe, normally they try
here,
to select from the next three any
one
of them or a blend
asterisk
of
mark, silica
first one
content,
with steel. That is because
we will
of when it comes to
the
the
need
need
of
of
high
high reactivity
reactivity
because of the low atmospheric
waning,
temperatures or
then
climatic
this
conditions
silica
and
content will
temperatures in the
become
winter
a
over there.
question mark over there.
Because
But
for us, we
that
have
we
a
need to handle it
problem
through
with
different,
controlling the temperatures
aspect.
because, but for them, they having
And that
pH
means
of
the
sand
sand should be
to
neutral.
the required temperatures of 20-25 is the biggest their
And this,
headache.
we are talking about
So
the
they
sand
naturally
distribution.
go for a very fast
You had
reactive
defined
and the way every binary system is a trade-off. The advantages you are seeing is fast productivity, productivity and low cost, but at the same time, the major shortfall. That means we can say the shortcoming of the system is presence of nitrogen in the system. The nitrogen coming from the part B, that is which contain methyl diisocyanate. Typically, the part B will have 7 to 8% nitrogen. And if you consider at the rate of 1% application, which is high, okay, then the core will have 0.7 to 0.8% of nitrogen. Okay. You know, melt naturally will have then everything is not getting burned and core sand is getting diluted into green sand mold, which will further accumulate nitrogen in the green sand. So if the combined limit of from the melt, from the core, from the green sand molding, it it exceeds the threshold limits, then it will result to you as a nitrogen fissure. If it is slightly on the borderline case, you may get nitrogen pinholing defects, and if it is on the excessive only on the higher side of the threshold limits, you will see it as a fissure defects in the casting at the subsurface area after machining. Mostly the fissures may not be visible by naked eye, but slightly after surface machining, you will be able to see. And this is nowadays with the Indian foundries using PUCB system, this is a casting problem being faced. And also another major shortfall is the reaction with the moisture. So this is part B, which have isocyanate, which is having multiple side reaction with the moisture. It can give you multiple byproducts. Anything undesired reaction can lead to very fast reactions, and which will give you very short bench life and strength loss. That will result to you as a friability and breakage of the core. So reaction of moisture and presence of nitrogen is two shortfalls of the system. And we have different types of amine to choose from, which is, I put it for an academic purpose, nothing great about it, but exceptly the first one, triethylamine, what we commercially use across the globe, across India, whereas in Europe, normally they try to select from the next three, any of them, or a blend of first one with steel. That is because of the need of high reactivity because of the low atmospheric temperatures or climatic conditions and temperatures in the winter over there. Because for us, we have a problem with controlling the temperatures but for them, they getting sand heated to the required temperature of 20-25 is the biggest their headache. So they naturally go for a very fast reactive amines, whereas for Indian conditions, it's a triethylamine, which is the normal option. Only just when look at the boiling point of this 80 to 88 degrees centigrade is the boiling point of that. So this is how some correlation with our process. That is why I mentioned over here. So polyurethane bond, this is how it forms the phenol resin, the part A resin, which is having a free hydroxyl group as the N polymer chain, and MDA, which will have NCO, that is a NCO group as the N-chain react to put together form a urethane bond. So that is why it is known as a polyurethane form. So with this much of knowledge about the binary system, you can look into the core shop management practices. So I did not go into the binary system detail. That is just you should know about it. So when you go to the core shop management process, we need to look at what are the major aspects. The major aspects one is the sand selection, temperature and moisture, that's impact, core making stages, and machine parameters and process parameters. Further, core storage, core dressing, core coating, that aspects we can further discuss. Today's session we will cover till the process parameters. And so we look at the core making process. It is a very schematic process. Sand grains, first liquid resin and hardener is getting coated with that. Then we pass amine gas through it. Then we again purge it out. During the purging operation, excess gas, amine, and some part of the solvent goes out, and a polyurethane bond which is formed between the sand grains. This bonds the core together, and we get a desired shape. So the major in the process, it is almost 98% sand. So 98% of sand will decide, or it will have the major say in how the core will behave, or how this system will work. That is why sand selection that will become the important aspect to consider. Under the sand grain, under this aspect, we need to consider sand grain shape, grain fineness number, particle size distribution, AFS clay and fines, pH value, acid demand value, temperature of the sand, and moisture content in the sand. This is you would take any big binary systems, people will talk about all these aspects, but very specifically, when you talk about PUCB binary system, we are very particular about all these aspects because it is a very sensitive system. If I talk about a no-bike binary system, moisture content, I may not give that importance, or a pH value, I may not give that importance because the binary system have the capability to absorb or work with that. But when we are talking about PUCB binder systems. This is very important. That is why I had very specifically put it. So the first four aspects, that is grain size, fineness, and particle density. This have a direct impact on the surface finish of the casting from the core side, and permeability of the core and the core compaction. When it comes to the remaining set of the aspects like properties like pH, acid demand value, temperature, and moisture, it have directly impact on the mix and bench life of the binder system, and also on the core strength. The mix and bench life means the workability of the mixed sand, or workability of the sand from the sand mix from which you can make the core. The PUCB process is typically we handle it as a batch process. We make a batch of sand, make the core out of it. That is how the bench life comes into play here. Okay, all these two aspects put together contribute to the core scrap, productivity, casting defects, and cost aspects. Okay, because if the mix sand bench life is low, your core scrap naturally will be low, and if it is low, your productivity, that is frequent number of sand mixes, and the core is friable, you can get defects like inclusion defects. Also, all these aspects contribute to your cost aspects, because for the sand wastages, lower sand bench life means your sand wastages, scrappage of the core, everything will be higher. So this is how all these aspects of sand have very important influence on the properties of the, the quality of the casting. So how it is each and every aspect work along with the quality of the casting. So under the best or the best practices, we are defining it as a sand quality. We always recommend you to wash, graded, and dry silica sand with a lower fines and clay content of core making. Very generic statement, okay? But this is any supplier will tell you this: washed, graded, dry silica sand with lower fines and clay content. And what is the AFS requirement? Typically in the range of 40 to 55. Lower than that, coarser than that means you need a lot of fine radiation level. Finer than means your fine radiation level also will go up. This minus 150 fraction and minus 200 fractions, this needs to be strictly controlled as per the specification, that is 5%, 1%. Clay content nil is the desired. As theoretically, there is nothing called nil, so we are allowing it, say it is 0.2% maximum. And ADV should be maximum 6 to 7 ml of 1 normal sulfuric acid, and silica content as higher the better, but 97% minimum. Here, one asterisk mark, silica content, we will, when it comes to certain casting defect like veining, then the silica content will become a question mark over there, but that we need to handle it through different aspects. And then pH of the sand should be neutral. Then we are talking about the sand distribution. So you had defined the specifications of the sand. When it comes to the distribution of the sand, that means the grain distribution, we recommend this 95% in the 4 or 5 screens with a bell curve shape, and this give you good packing and resistance to expansion defect, because always a wide screen distribution give you better compaction and expansion resistance. The more the expansion resistance, you have defects like scabbing as well as veining, both will be under control. Okay, if you try to use a single peak sand, then your possibility of getting veining defect is much higher because it is less expansion accommodative. Then come to moisture content. PUCB system is very sensitive for moisture. Okay, so any system with the less than 0.2% moisture is required, and also sand transportation in the foundry should be minimal, because we typically see when we receive at lorry level, the fines are very under control, but by transporting it inside the foundry from machine to machine, from the sand storage to the machine hoppers, we find typically 2 to 3, sometimes even 6 to 7 AFS is changing because of the uh, sand degradation during pneumatic transportation. So this is also very important design aspects, and you need to be mindful about it because the more fines in the sand will lead to higher addition levels, requirement of higher addition levels, as well as uh, expansion scabs, scab defects. All these aspects comes into picture here. Sand permeability, typically 100 to 150. This reduces the gas defect as well as scabbing defect, because there is a direct correlation between the sand permeability and the scab defect, and also pinhole gas defects. They are directly proportional to sand permeability and hence the core permeability. Okay, addition level being the same, sand permeability directly translates to core permeability. The more the permeability of the raw sand, the more the permeability of the core. So when you say if you can control the bottom, that is 200, 300 and pan portion less than 5%, then your permeability can be achieved, even with a better spread and distribution with a finer AFS number. So because of the system limitations, we try to go to coarser side to control the fines, but the ideal way is to move to the finer side of the AFS by controlling the finer side of the spectrum of the screen distribution. Sand grain shape, it is again academic in nature. Okay, to understand that there are different shapes in the sand, because for us to get round grain of sand, it is difficult because typically Indian sands have angular to subangular shapes. So we have to leave it what we have. But nowadays, there are a lot of means of even converting, treating the new sand to get even though not perfectly spherical, but preferably round shape grains. Like if you can do a, what you can say, sieve de-dusting. During the de-dusting process, sand grains collide with each other and to give you a round, angular to round shapes. Okay, there will be certain amount of silica loss over there, but the grain shapes are getting transformed from angular to round shapes, which will demand for lower binder addition level, because round grain shapes demand less binder. Also, round grain shapes give you better flowability of the sand. The better the flowability of the sand, and the round in nature gives you lower addition level and a better flowability, that can give you very thin section core, successfully making 2 mm, 3 mm, 4 mm cores. If you want to shoot it perfectly with good compaction, this aspect need to be in mind. If you have a very because round grain with the uh, uh, means lower addition levels give you better compaction, and hence, but compaction have a impact of lower permeability. But if you can achieve that compaction with the lower binder addition levels, that will take care of your permeability aspects, which will give you better casting surface finish as well as a lower gas defect. And definitely the round grains will give you better casting surface finish. Also, when you look at the sand grain distribution, one more aspect which needs to be mindful is about the specific surface area. So here I had to give you the example of two sands.
Please mute yourself.
So here I had given you an example, whereas the sand A and B both have the same GFN number, that is grain fineness number, that is 55. But the distribution is different. One is more towards a single sieve, maximum in a single sleeve, whereas the other one is having sand A is having spread over the 4 sieves. So if you look at sand A, the total surface area of sand A is higher than sand B. That means sand A is having 4% higher surface area. So sand will demand higher binder addition, but it will give you better compaction. Lower probability, but it will give you better surface finish. So when you select the sand, the grade AFS number or grain fineness number is only one indication, but you should be mindful about the total surface area also. So foundries will say they are also using 55. I am also using 55. Their addition level is 0.9. Why I need to use 1? These are the all typical questions we being faced. But it is not only about the AFS number, it is total surface area. There are furthermore aspects to be considered over here. Then grain fineness number. Okay. So grain fineness number, as the grain fineness number increases. Okay. The total specific surface area also increases. So that means the sand become more and more finer. Your surface area of the sand grains to be coated by the binder, it increases linearly. The more you fine side you may move, it will demand more application rates. That means more additional well, and it will reduce your permeability, but it will improve your surface finish. So this is again a trade-off where which you have to decide where surface finish, you need to get it from the sand itself, or you need to get it through a use of a proper refractory coating, and to achieve a better permeability and a lower addition level. So moving towards the finer side is also not the solution to the coarser side. When you see, even though surface area is less, but the sand to sand contact points or the bridging points reduces. That also is so. It is strength values. If you plot like this, it is not linear. You will see a bell curve strength plot graph from 30 to 70 here also. That means in the range of 45 to 50, you will get the peak strength with the same addition level. So if you consider 0.8% addition level and use this sand having AFS variation from 30 to 70 at the same application level, you will observe the peak strength at the 45 to 55 region. Thereafter, you will see the strength will reduce. Before to that also, the strength will be lower. So this can be further explained by, okay, before going there, then coming to the moisture part. Use the sand with a low moisture content. Visually, sand may look dry because beyond less than 0.5% sand, moisture in the sand is not visible or with your naked eyes or detectable by naked eyes. So that is why you have to be very careful about the sand, moisture in the sand, silica sand itself, and purging air. So a compressed air used, this also should be free of moisture, and ideally compressed air with a dew point of minus 40 degrees centigrade is recommended by the machine operators for getting a we can say dry air. And also the temperatures and the machine should be maintained at such a level that residual amine retention in the core needs to be avoided. If you look at this, the last core, there is a lot of white spot you can see near the blow ports, which is also the gassing port, where the white coloration indicates the amount of literally liquid deposition of amine over that area. This area becomes so weak that area becomes the epicenter for the moisture attack for the core when you store it, and the degradation of the core will start from that point. So that is also another aspect, and also improper drying of the coating. So that also is another source of moisture for the binder system PUCB. And also when you select a binder system, PUCB binder, you should select a high hot strength binder, which is nowadays normally available, which is now because polyurethane got introduced to India in 1980s or late 80s. And so almost 45 years we are working on this. From what we got introduced in 1980s and 1990s, from there a lot of improvements have been done over this binder system with respect to its humid storage resistance, benzylize aspects, the hot storage properties, especially with the thin section, the viscosity, the flowability, lot of aspects, the sticking properties of the binder system. All these aspects has been undergoing a gradual improvement over a time now. So if you compare a conventional binder system, at least 20 to 30% higher strengths and high hot strengths and cold strengths are nowadays available. So these are the major important considerations in the process. once again, coming back to the sand, I was just talking about the grain distribution. Just consider, say, if you have a homogeneous grains, like a single sieve distribution, like in your 60 sieve or 70 sieve, you have majority 60-70% of your sand retained. Just think uh, uh, about this as a two-dimensional picture with the actually in between the sand grains, you can see only four bridging points. Okay, resin, the black colored grain, the whole shape is considered as a sand grain, which is covered with a resin coating. Now, unless this resin coating of two sand grains come in contact, it will not bridge together, or there is
Mail அனுப்பிச்சிருக்கேன் 4 print out. One fresh paper எடுத்துருங்க.
So unless it is a in vicinity and the catalyst presence over there, then only it will corrosive. So for a homogeneous grain, you can see literally only in the 2D dimension, you can see only 4 bridging points. But you think about a heterogeneous grain, wherein which you have a finer grains and a coarser grain, wherein which the finer grains are going and filling in the cavities in between the coarser grains. You can literally see instead of 4 contact points, there are 8 contact points. So this will give you multiple bonding sites across the sand grains, which gives you more bond strength. So this is one reason wherein which when you goes to the coarser portion of this AFS number, your bonded strengths are going down or your resin demand increases because the less number of contact points. When coming to the another aspect is when it's homogeneous grains, there is a large void spacing between the grains where which you will get a result to a rough surface, and it will require you to look at these surface areas, you need more amount of coating to get the desired surface. But in case of heterogeneous, you have a very thin curve or thin area to be filled. So that is also another point, and which is sometimes foundries use with the 16, 17 before cup viscosity. One foundry uses, and other foundry says if I use that, I can still see the core surface. This is one reason the sand background itself is not absorbing and having full of curvatures. It will require you to use a more amount of coating and maybe multiple layers of coatings. So when you look at the surface finish comparison, a finer grain of sand or a heterogeneous grain distribution will give you better surface finish. When it goes to more to homogeneous grains, it will give you more and more rough surface finish, because even coating have a limitation to take care of it. The first thing what we are looking at the background of the mold and core itself, so that coating can do its function of other properties like veining resistance and other aspects. So this is again an illustration where when the GFN increases, that the grain fineness number increases, your binder bridges per unit volume increases. That means the strength, the specific surface area also increases, but the number of binder bridges per unit volume increases, the specifics, the binder strength also increases. So this is applicable to certain extent up to 50-55 area. Beyond that, you will see this will start reversing because the specific surface area impact will take over the binder bridge impact. So that is why we normally recommend in the range of 45 to 55 as the cutoff point. Clay already explained. Clay is unwanted element as far as the core is concerned, whereas we do add clay to the molding sand as a binder. But from the side of core, it's an unwanted element because it will eat away the binder, because clays are very absorbing. And the thumb rule is 0.1% clay will demand 0.1% more additional level to give the same strength. So as far as possible, keep it very minimal, and also -50 and -100 fraction to be kept as far as below the 5% to give you the better permeability and to produce the core scrap. But if you have a high clay system, then if the binder addition level is not increased to compensate for that. Then you will have friable cores which can lead to inclusion defects. And if it exceeds certain levels, it can give you gas defects and scab defects. Okay, because gas and scab, there is a, we cannot say direct control, indirect control of correlation between scab and gas defect. Also, pH of the system, the sand should be neutral as far as possible, because the more acidic, the lower bench life, the bench life of the system is getting, it will get affected. Then it will lead to friability of the core if you made after a certain time. Then purity of the sand, 97% silica. Then remain the rest of the things we normally call it as gang elements, which is there with the silica, cannot be removed. Source to source, where from it is sourced, this gang element can vary, but inherently it will be there. Out of that, the first 4 or 5 gang elements are known as favorable ones, because it gives you improved veining resistance. Whereas the last 4 ones are the enemies, because they are flexing agents, reduce the refractiveness. Especially if you, even with a higher purity, if that last 4 elements are present, that will give you, reduce your sintering point of the sand, which will give you sand fusion defects. Also, if you try to reclaim this sand, this will act as flexing agents and change the surface morphology of the sand grain, reducing the bonding strength of sand for the subsequent reuses. So another aspect is a core complexity increase. As the core is becoming thin and thin, the area difficulty is to blow and get a uniform core density or core compaction at the areas. This core compaction difference may not be visible to naked eyes, but if you are dipping in the water-based coating and observe the core, the absorption, definitely it will tell you where are the weak spot or the less compacted areas. Definitely we will not use such a core, because we will go for a high viscosity coating to compensate for that. But if you want to see, if by naked eyes you cannot see a diluted coating, if you dip a core and the absorption across the sections are uniform, we can say core compaction and density is similar. And core scrap we are already discussed, and the inner passage cleanness, because it is very difficult to access these areas through tools for cleaning. So internal passage cleanliness is an issue with the more increasing core complexity. And one more aspect is the particulate matter retention. These are nothing but fused mass of coatings, which is retained, which should go normally if short blasting or a short reaches over there. But as the core section becomes so thin and complex, it is difficult for the particulate matter to be removed. So this is also another challenge. So we have different ways of looking at it. If you want to have uniform core packing density, you should select the good quality of binder system with a low viscosity, high out-of-box strength, and also high coated core strength. Okay, it is a trade-off between out-of-box strength and coated core strength. But for getting a better compacted core, you need to select a trade-off between these two based on your core section thicknesses. Then foundries try to use, when the silica sand falls short, people try to use advanced sand and chromate, and also multiple other sands like heavy sands or alumina bead sands. This is basically to improve. It is basically we are trying to cover up the deficiency of silica sand. When I say silica sand, the silica sand available to us in India, because I will not say all the sands across the world is similar, but we have silica which is available to us, and this we have to live with that. So for very thin sections, when we fall short of the strengths, the record handling strengths, then the flowability aspects, then we think about advanced sand, chromate sand, or heavy sand, or alumina beads. That is one aspect of it. Then one aspect is the good PUCV core shop management practice is what we are discussing. understanding and optimizing the process. And also use a specially designed rheotic coatings based on your, we had seen two type of aspects. One is retain particular matter aspects, retain particulate matter, as well as internal passage issues. So we have specially designed rheotic grade of coating, which will take care of this internal passage cleanness and retain particulate matter, which is another subject for the discussion, which I am not covering today. Then to illustrate the impact of moisture on the mixed sand, bench life, as well as the tensile strength. If you look at this, presence of moisture varying from 0 to 0.5% in the sand, the strength can drop from 250 psi to 50 psi, that is 1/5. So it is inversely, it is impacting. The more you moisture content, the strengths are dropping drastically. Also, the bench life of the mixed sand. So you had seen the reaction of MDI, that is methyl diassociated with moisture. So instead of an MDI, NCO group is not a very reactive group, and this preferential reaction towards hydroxyl group is not very good. The moment you get some other elements, slight amount of acidity, moisture presence, their preferential reaction direction will change, and instead of reacting with the polyol which is present in the resin, it will try to react with and form side chains, and it will get wasted rather than getting into the formation of a polyurethane bond. That is why traces of moisture is also danger to the polyurethane system. And next aspect is the temperature. Sand temperature also have a very big impact on the polyurethane system performance with the two aspects. That is, one is short bench life and another one is friability. Okay. When you sand temperature, ideally should be controlled in the range of 25 to 32. And beyond 32, we don't recommend you to use even under Indian conditions, the sand temperature. I know currently there is no specific controls put over there, but getting sand below 25 is normally is not is a probability in India, but above 32 is a big possibility. But if you are using that sand, but be mindful that we are impacting the bench life of the sand, and it can lead to the friability of the core. So here is again 10-degree rule applies. That is every 10-degree increase in the sand temperature, the bench life becomes half because the reaction speed doubles. So it brings the bench life to the half. So for example, if you are getting a 150 minutes of bench life for a mixed sand life at 25 degree, hardly what you will get is 17 minutes in 55 seconds. The biggest challenge here is in the shop floor. The person who makes the core, he is not aware of any of these things. He is given a task of making the core on the machines. He is not mindful about or aware about the sand temperature. He will keep on blowing the core without knowing whether the bench life is there or not. So that is why it is, from our perspective, very important to control or put controls in place that if the temperature exceeds these limits, there should be a cutoff mechanism, or there should be some mechanism to control it. Also, this is the role of the special sand. We had seen the advanced sand or ceramic sand. The first graph indicates a typical additional level, that is a 0.9% of additional of PuCP silica sand. Typically gives you 200 to 220 psi tensile strength, whereas if you reduce it to 1.6 psi, the strength may drop to 180, 160, 180 psi. But if you use roughly 20% chromite sand, typically thus at 1.6% additional level, 210, 210. That is better than silica sand, the strength improves. So there are two aspects here. One is the higher strength, second is the improved probability of the sand. So this is where one aspect which will come to our help when we are making very thin section cores, where the flowability can be improved with the higher strengths by slightly changing the sand additives. And the similar impact, not to this extent, can be obtained by treating the silica sand itself. If you are getting a very angular silica sand, if you can do it through a de-duster, angular nature of the sand can be made into a certain amount of round shape. So that to certain, not to this extent of chromite sand. What is going in the favor of chromite sand, it is density as well as the grain shape, which is perfectly round in shape, okay, and high density. So these two aspects go in the favor of chromite sand to give you a lower application level as well as the better flowability. So working on silica sand also we can come to certain extent near to that, but not to the same extent. Sir, is there any time limit or any aspects like what is the cutoff time?
Sir, we can go forward, sir. I don't think we have an issue. Probably another 10 minutes also should be fine.
Okay, fine, no problem. Okay, this is the different stages of core making. The first stage of mixing, and already we talked about the sand, and chemical ratio should be based on stoichiometric ratio balance. That means we said 50-50 balance or 1:1 ratio should be the balance. 5% here or there is not an issue. Beyond that, you will be either wasting one part excessive because 60-40 ratio, yes, is Europe and people follows that, but the resins needs to be prepared for that, balancing the stoichiometric ratios. What we most of the supply, every supplier in India we supply is a stoichiometric ratio balance 1:1. So unbalancing the ratios is not going to give you benefit, rather it can going to be harm. And if you are going by a batch mixing, part B should be added first. Okay, these are all basic things, but many times now we are 40 years working it, and many of the steps are overseen. That is why, even though silly things, I am repeating that. Part B is low viscous, easy to mix, and it should be the first in the sequence. Even for a batch mixer addition level, it should be the dosing. It should be B should be the first one to add. Even in a continuous mixer, the first what should be B, then followed by A. This is to give you effective mixing. And if it is a batch mixer, RPM above 80, and the higher the RPM, the better, because many a times we did compare European application rates of PUCB versus India. Definitely, the sand quality is one aspect. Okay, the European sands are much better than Indian sand with a round grain shape and distribution. But one more aspect we are overlooking is the mixing. In India, typically we try to use S-blade mixers or maximum bowl mixers, or which is medium intensity mixers, whereas most of the foundries in Australia or in Europe, they have continuous mixers which work as 1500, 500, 600 RPM, which will give you much better efficiency of the mixing. And also avoid excessive mixing and heat up the mix sand. And mixing batch size should be controlled based on the core size. And this already explained, not more than 8 to 10 shots of sand at a time. Okay. And so wherever possible, high intensity continuous mixers can bring down the application level. Okay, that is if you are having already one, try to increase the RP levels. It is possible. Otherwise, when you are considering your net custom capex, continue try to go for a better mixing equipment. When shooting and plowing, the sand magazine should be always 2/3 full. Okay, you should not try to empty out it every time. That is the cycle in which every shot there is a refilling operation. Don't try to override that. And magazine size, core weight, this already we had explained. 5 kg, 15 kg capacity should be fine, but not 30 liter. Shooting pressure 3 to 4 bar, and minimum the best, but not less than 2 bar. Higher the shooting pressure, the more the wipe off of the resin happens, and which is sticking to the core boxer sides, and that will lead to a lot of build up on the core boxes. Then you will lead to lot of rough surface on the core surfaces. So which will
Sir, we can go forward, sir. I don't think we have an issue. Probably another 10 minutes also should be fine.
Okay, fine, no problem. Okay, this is the different stages of core making. The first stage of mixing, and already we talked about the sand, and chemical ratio should be based on stoichiometric ratio balance. That means we said 50-50 balance or 1:1 ratio should be the balance. 5% here or there is not an issue. Beyond that, you will be either wasting one part excessive, because 60-40 ratio, yes, is Europe and people follows that, but the resins needs to be prepared for that, balancing the stoichiometric ratios. Most of the supply, every supplier in India we supply is a stoichiometric ratio balance 1:1. So unbalancing the ratios is not going to give you benefit, rather it can going to be harm. And if you are going by a batch mixing, part B should be added first. Okay, these are all basic things, but many times now we are 40 years working it, and many of the steps are overseen. That is why, even though silly things, I am repeating that. Part B is low viscous, easy to mix, and it should be the first in the sequence. Even for a batch mixer addition level, it should be the dosing. It should be B should be the first one to add. Even in a continuous mixer, the first pot should be B, then followed by A. This is to give you effective mixing. And if it is a batch mixer, RPM above 80, and the higher the RPM, the better, because many a times we did compare European application rates of PUCB versus India. Definitely, the sand quality is one aspect. Okay, the European sands are much better than Indian sand with a round grain shape and distribution. But one more aspect we are overlooking is the mixing. In India, typically we try to use S-blade mixers or maximum bowl mixers, or which is medium intensity mixers, whereas most of the foundries in Australia or in Europe, they have continuous mixers which work as 1500, 500, 600 RPM, which will give you much better efficiency of the mixing. And also avoid excessive mixing and heat up the mix sand. And mixing batch size should be controlled based on the core size. And this already explained, not more than 8 to 10 shots of sand at a time. Okay. And so try, wherever possible, high intensity continuous mixers can bring down the application level. Okay, that is if you are having already one, try to increase the RP levels. It is possible. Otherwise, when you are considering your net custom capex, continue try to go for a better mixing equipment. When shooting and plowing, the sand magazine should be always 2/3 full. Okay, you should not try to empty out it every time. That is the cycle in which every shot there is a refilling operation. Don't try to override that. And magazine size, core weight, this already we had explained. 5 kilogram, 15 kilogram capacity should be fine, but not 30 liter. Shooting pressure 3 to 4 bar, and minimum the best, but not less than 2 bar. Higher the shooting pressure, the more the wipe off of the resin happens, and which is sticking to the core boxes sides, and that will lead to a lot of build up on the core boxes. Then you will lead to lot of rough surface on the core surfaces, so which will require frequent cleaning. And your shooting pressure should be maintained at least 1.5 bar lower than the clamping pressure, because many times we say that our amine consumption is very high. Amine consumption, many of the times the reason for amine consumption higher is leakage, and one of the reason for the leakage is during the shooting, the clamping gave away. So try sand, small grains of sand get into the parting lines, and that parting line is good enough for the amine to pass through. So that is why we need a firm. So if you are pneumatic clamping, which you have a limitation of 5 to 6 to 7 kilos, then your shooting pressure you should be mindful. If it is a hydraulic clamping, then there is no issue. And shooting time should be as minimal as possible and as required for geometry. And that you should not double shoot any cores, and excessive core shooting will give you wipe off. There are different type of amine generated, the bubble types, the automation type. Nowadays, the bubble types are not in use. Most of what we have is one is with automation stage, where in which we go through 2 stages of gassing, that is low purge and high purge. A low purge is to allow the amine to spread across the core at a low volumes. And the remaining next stage of high purge is to take away the amine out of the system, out of the core fully, because retained amine in the core can bring down the life of the core. Also, purge air temperature should be above 70 degrees centigrade. and you had seen the amine, the boiling point is 88 degree. So that is why I recommend 70 to 80 is where you will have enough vapor. You can create sufficient vapor pressure to carry that amine through the core effectively. If you use purge air temperature lower than that, you can see condensation in the gassing lines. Then it will accumulate sometimes and come to the core directly as naked amine. And you can see the type you had seen on the white patches on the core box, that type of it. It should not come to the liquid amine should never come to the core. It should be always atomized. So that is the importance of purge air temperature. So purge air temperature 70 to 90 is also okay, but not beyond 100. Gassing line should be insulated. This is all machine concentration. Amine gas ratio typically should be 8 times of amine. And air flow and gas process should be tried at 40 degrees centigrade. Then mixer cleaning. Mixer cleaning is one area which is very systematically or periodically done jobbing foundries for their mixers, but it is mostly overlooked area for iron mass foundries, especially for PUCV core sheet. But we recommend this mixer cleaning every ship and check the blade wear out and excessive buildup on the side walls, and also check for the resin bowling, which normally will not be very visible to the naked eyes, but other type like other specific blowholes on the areas, random blowholes on the casting surface areas will tell you the possibility of resin bowling. This is more to happen with the S type of blading. And the chemical dosing to be done by weight, not by volume. And sand transportation, you avoid the excessive sand transportation pneumatically. Venting. So since we are out, sir, should we close it and we can take it on to the further sessions further, because it is already time is close. What do you think about it?
We'll close it and then we'll keep the floor open for some questions.
Yes.
And then we can proceed with that.
Okay.
So already Ajit had posted 2 questions. I'll just read it out for you, sir. How to measure SiO2 purity in sand for better refractory method?
You are SiO2 with the silica content you are talking about?
Correct.
Okay, silica content, there are analytical methods which is little cumbersome to analyze. That is basically you treat it with HF, basically etching with the HF. Then you repeat this cycle for over a period of time and you effectively remove the silica and then weigh it. That is the analytical method. But even XRF also can give you an idea, but you have to do it for multiple calibration, because of XRF, if you can do it multiply and establish the process with the people or laboratory who are doing it, then you will be able to correlate it, because XRF will not give you the exact reading. So you have to do a couple of samples both with XRF and analytical method, that HF method. Then you can correlate a relation.
Ajit, do you have any other question? Sir, he has also asked, in GFN analysis, what would be the below 100 mesh sand size recovery percentage? Is it important to monitor and any specific range for it?
Can that question be repeated?
In GFN analysis, what would be the below 100 mesh sand recovery percentage? Is it important to monitor any specific range?
No, I am not clear about that question. What he meant by what is the recovery percent means in the GFN analysis is when you do the analysis, you will get it. Okay, you will be able to analyze and you will be able to know it. But what do you mean by recovery? I am not sure. He can ask that, clarify that.
Ajit, you can unmute yourself and ask your question just to clarify.
If he is talking about molding sand.
Yeah, sir, molding sand. Yes, sir. We are analysis. We are making GF analysis. That will be peak, double peak, single peak. Trend will become. No, sir. So Always below meshes are there in below 100 mesh. Any specific this much of percentage of sand retention will be there. Anything is there, sir? Is it monitor? Is it required monitoring? Any dust particle like that structure is observed? No, sir. That is any affecting to casting quality. So that percentage we want to know.
Okay. So you are talking about the molding sand, right?
Yes, sir. Yes, sir. Yes.
Okay. Molding sand, when you analyze your grain fineness number and the minus 100 is of the return sand or the molding sand, then you will get what exactly is there. But what you get is after the dust extraction, because definitely minus 100 fraction, definitely it will go out during the dust extraction process. Okay. So what exactly is there in the return sand in the silo and which is going to the pooling dust extractor, that will be definitely there will be a drop because dust extraction will come. But it is from the molding point of view, that sand retention is very important aspect to have your surface finish aspect from the molding point of view. Is it what you are meant to?
Yes, sir. Okay.
Is it your question something different?
Yes, sir. Yes, sir. Same. What you are explaining?
So what you analysis, which sand you analyze, which is going before the dust extraction, after the dust extraction, what you will have in the silos will be after what you see. Then sometimes knowingly, if the surface finish there is an there is an improvement, then people normally check the MOA of
Is
the
it, sir, any
fine
particular
sand.
range is bet for that retention material?
We are talking about the molding sand.
Yeah, that only, sir. Molding sand. That below 100 mesh we.
Let's see, that 2 to 3% normally we control.
2 to 3%. Okay.
But when it is talking about the core making sand, it should be minus 150 should be strictly below 2%.
150 below 2%.
For core sand. Okay. For a molding sand, we need surface because there are two aspects here. One is molding sand, one is your molding sand AFS itself will be at roughly 15 to 20 AFS higher than your core making sand. Second thing, your fines are kept for a purpose, for the surface finish. Cores are coated to get your surface finish. But there is mold, there is no coating. What you get the surface finish is exactly from the molding sand fineness number.
Okay.
So,
okay, sir. Okay.
Right.
So
we'll have one more question and we can wrap up the session. Is there any other question?
Mr. Ramaya sir, can you please off your camera? Switch off your camera.
So anybody else has any questions, sir? All right. Okay, sir. I think
one question.
One more question. Okay.
Yeah. So this is Nitin calling from Gokul Gulzar. I mean, we don't have a desiccant type dryer which having the dew point of what you said minus 40 or something. The normal dryer, which is doing around the dew point maybe somewhere around 8 degrees or 4 degrees max. So, what is the effect of such kind of a air on the core quality?
So you are talking about the air dryer, which is giving you the compressed air, means purging and shooting air, right?
Yes.
Okay. If the moisture is higher, the core friability and core storage strength will drop. Because that also depends on the how much moisture is going inside. Suppose you are putting 0.9% and 0.1% water is going from that whole process of dryer. I mean, not having a dryer, that will have an impact on the strength and bench life of the core. your core storage stability will be lower and apparently strength will be lower.
Okay. Hello.
We'll have just one more question. I
Oh.
think we have
Yeah.
had a very good session so far. So we just have one more question and we'll try to wrap up.
There is some few questions in the chat room.
Yes, I read
What
those.
is,
Yeah.
what is the mixer cycle time for good mixing resin AB and for having good bench life? Okay, this is a typically if you use a S-type blade, S-blade mixer, typically it is a 60-second plus 60-second. Okay, that is 1 + 1 2 minutes, and this we can further subsequently brings down as the RPM goes up. And if you think about a continuous mixer, the total retention time of mixing time inside the barrel will be less than 2 to 3 seconds, maximum 4 to 5 seconds. So that is the mixing time for a intensive continuous mixer. So mixing time is a function of your mixing intensity. Because it is already built up, then you have to use new fresh sand addition. You have to increase to diluting.
Okay, I think we can wrap it up now. I hope everyone had a really good session. Special thanks to our speaker, Mr. Mathew sir. I think you're very wise to select specific topics instead of going over a very general sand core process. You went specific, and I think it was really helpful for all. From the amount of responses and people who were interested, I can see that it was really helpful. So I thank you once again. I thank you on behalf of IIF Chennai Chapter and Andhra Chapter. So we'll be having more technical sessions in the coming weeks as well. So everyone, please be following our pages, WhatsApp and Facebook page, and we'll keep you updated. So thank you again, sir.
Thank you.
Thank you, everyone.
Thank you.